Nika always finds very clever ways to get around like worst case hardness results in machine learning. Always envious of the results. So happy here.
Thank you very much. Today I'm going to tell you about that lying, not trustworthy calibrated forecaster. Or okay. But if you're not into scandals, it's okay. We're just really going to be talking about how would you design measures for calibration that are truthful. So what do we mean by calibration, truthful, and even predictions? Before I talk about that, this is joint work with 3 amazing researchers. Ming-Da Chia, who was a postdoc here, continuing his postdoc at MIT and starting faculty position at UMass. Kunhei Yang and Eric Jia, who could have been postdocs here, but are PhD students here. And in fact, the talk is based on amazing talks they've been giving on the same topic. Okay, so what do we mean by event forecasting? The online probability forecasting is a scenario when you have a forecaster who is interacting with nature, is trying to forecast the probability of some event happening, make some forecasts, then make some observations about what the actual outcome was, and then refines his forecast. And these online predictions are really the basis of how we think about providing forecasts and predictions in a changing world, where we may be dealing with an adversary in the form of nature, or even a perfectly well-behaved stochastic world. And they're sort of everywhere. You can think about weather forecasting when somebody's telling you what's going to happen tomorrow, the chance of rain versus sunshine, to sport betting, gambling, online advertising, all forms of economic forecasts, election forecasts. All of these are the forms of forecasts, like when you actually want to know the probability or express the probability of some event happening. But of course, events that are probabilistic are really hard to think about what a good forecast would be. So one way to think about this is to actually think about accuracy conditioned on the actual forecast being made, or some notion of internal consistency. So what that might look like is we have T many days. Every day, the forecaster has to make prediction about an event. So let's say that we're trying to figure out what is the probability that it rains today. So it makes a prediction, say 0.75, and then the nature actually reveals what the outcome is. So it happened to be rain now. Then tomorrow we make another forecast, 0.5 perhaps, and then again, nature reveals what the actual outcome is, sunshine this time, and so on and so forth. So it's like a repeated game. The forecaster is making some forecast, and then the nature actually reveals what's happening. So one thing you might want from this is that you look and you say, well, if I'm evaluating this forecaster, at least I want the forecaster to really mean what they say. So what this could mean is that I look at the times that the forecaster predicted 75% chance of rain, and at least I want to make sure that the forecaster is consistent in the sense that condition on 75% being predicted, indeed 75% of the time it rained, okay? So this is saying that conditions like an empirical conditional probability. And you don't need to even just think about 0.75. You want the same thing out of 0.5. You look and you say, well, the times I predicted 0.5, indeed, half the time it was raining, half the time it was shining. This is a notion of internal consistency, and it's the minimum requirement for predictions to be meaningful, to mean what they actually say. This is called calibrated forecast. It goes decades back now. It was introduced by David in 1982, and essentially we say that a sequence of predictions P1 to PT are perfectly calibrated for the actual outcomes X1 to XT. If for any value that you predicted alpha, this alpha is 0.5 or 0.75, alpha is indeed the empirical conditional probability of the event happening. So the empirical conditional probability is number of time steps you predicted alpha and it did rain indeed, compared to the number of times that you predicted alpha. So this is what it means to be perfectly calibrated. And calibration has been long taken as essentially a form of reliability. I was saying it's a form of internal consistency, or in fact, the fact that your calibrations are trustworthy or reliable. It's partly because this internal notion of consistency and reliability means that, calibrated means what they mean, but it also means that it has some good decision theoretic properties. This was shown by a number of works in, late 90s. For example, if you take these calibrated forecasts and you act based on them, you don't have what is called internal regret. You don't regret the decisions you made. You don't want to go back in time and change those decisions. This is also shown in the fact that if agents are sort of working together based on some calibrated forecast of each other's actions, the empirical sort of frequency of the actions they're taking converges to different notions of equilibria. For example, it converges to correlated equilibria if all of them are using these calibrated forecasts, and that was shown in 97 by also Foster and Laura. But we've also shown more recently that even if one of them is kind of using these forecasts, you can converge to other good game theoretic and decision theoretic notions. And on top of that, these calibration metrics are meaningful in the sense that even if you're dealing with an adversary, you can asymptotically make sure that you have no calibration error. So asymptotically, on average, essentially, you can have forecasts that are calibrated. So this is all the good things about why calibration is taken as a sign of reliability, and it's a very useful metric. But when you really think about reliability, we might want other things from a calibration or from any measure. Beyond decision theoretic measures and properties, you might want reliability to mean that you can just delegate this task to someone to do it for you. You can ask them, can you please go and find a calibrated forecaster for me? And you can trust that that work was done well. What that might mean is that if the forecaster you are hiring actually happen to know something about truly the nature, like how these events are generated, they're incentivized to really use all of that knowledge and reveal that knowledge to you, rather than trying to game the system. In other words, you want these forecasts to be truthful. So the question we're asking in this talk is that, are they truthful? And to really answer that, of course, you need to understand, how do we even evaluate calibrations? Like if I were to delegate this, or if you were to give me a set of calibrated forecasts, how would I evaluate whether you did a good job or not? And those are done via things that are called calibration measures. Calibration measures are just functions that are used for evaluating how far forecasts are from that perfect calibration, that definition of David from 1982. So let's look at how you might want to think about a calibration measure. So this is the same kind of outcomes that we had before, but the predictions are now slightly different. Instead of 0.75, I have 0.8. And if you look, condition on 0.8, my empirical frequency is 0.75. So there's 5% sort of bias here. Same with when I'm conditioning on 0.4, the actual empirical probability is 0.5. So there is 0.1 sort of empirical bias there. If you add all of these biases up cumulatively, that is something that's called an expected calibration error. So it's the cumulative bias when predicting alpha for some overall alphas. In other words, or more mathematically, essentially, you look at the empirical bias that you have, and you pay how many time steps you had that empirical bias. So this is by far the most well-accepted way of measuring whether something is calibrated and how far from calibration is. This is also sometimes referred to as L1 calibration error. But there are other calibration measures. I'm not going to go through all of them, but essentially the way people like to think about these calibration measures are that these are distance metrics or distances from perfectly calibrated forecasts. So what you might want from these calibration measures, and we are taking calibration measures kind of like we're taking a very broad perspective on them, is that you want them to be to actually be complete and sound. That's like the bare minimum thing you want from a measure. What does completeness mean? It means that if something is good prediction, so it should actually receive very low penalty in terms of the measure we chose. One particular way to think about good predictions, like we're just thinking about this like minimal assumptions possible, is that if everything was actually generated by some nice Bernoulli and you predicted that nice Bernoulli, you want to make sure that your calibration measure, the penalty that you're receiving, is truly vanishing as the number of time steps increases. So that's completeness. Soundness is sort of the other side of this, when you want bad predictions to be penalized. So what are some bad predictions? So for example, at every time, if everything, let's say, was deterministic, and you predicted exactly the opposite, that's truly a bad prediction. You better be paying omega of t penalty. But also, if you're sort of mistaken and biased in a very obvious way. So let's say that, again, everything was a Bernoulli, and instead of predicting that Bernoulli, you predicted a Bernoulli that was off by another constant. Then again, you deserve to receive a penalty that's omega of t. So these are, we think about them as sort of minimum, desiderata for what a calibration measure has to actually be. Like, it has to actually measure calibration and has to be sound and complete. And indeed, almost all calibration measures that one think about satisfy these things, Yeah.
So it seems like, soundness seems kind of weak here, no?
Both of these are quite weak. And the reason we make them quite weak is that this is not the main thing we're trying to do. We're trying to say that either you're not sound and complete or you're not truthful in some sense. Okay. So our focus is on the other side.
Well, so one of the things that I always have trouble with this is that, like, you can be calibrated even if you don't know anything. So somehow, like that Foster-Bora is like a positive result, but it's also kind of a negative result depending on how you look at it. Because, like, if you and I are both predicting the weather, but I know something about it, you don't, both of us can still achieve calibration.
This is a perfect comment on which one of you was better and which one of you should have been rewarded better. And that's what we are going to see. So perfect comment and perfect question. Just to say it for people who might have not heard it, is like, these are indeed quite weak because they're not our main contribution. These are just like us formalizing as weak as possible assumptions on what you want from a calibration measure, because you could just have a calibration measure that's constant and it's meaningless. But then you might ask, how do you actually, measure who is a better calibrated forecaster? But okay, so these are actually satisfied by almost any calibration measure. And in fact, all of those calibration measures, there's this common belief that you can sort of trust them and they're reliable because of what I said earlier. So the question now that we have calibration measures, are that if we take completeness and soundness as given, can we actually trust these and anything that has low calibration measure to also be a good calibrated? In other words, this is like essentially what Ankur was asking, is that if somebody actually knew something about the underlying generating process and they're being measured, the quality of the calibration that they're giving us is being measured by these calibration measures, are they incentivized to tell us the truth? This is where reliability and truthfulness start to diverge. And from the title of my talk, it shouldn't be a surprise that calibrated forecasters are lying to you. So truthfulness and reliability are not the same. But let's see, why might that happen? Let's think about the scenario. This is the nature. I'm giving you a very perhaps weird nature. T-time blocks are divided to blocks of size 3, where in the first slot, you actually have a truly random half and half coin. And then the second and third are just the outcome is deterministically 0 and then deterministically 1. So if you're a truthful forecaster, in a sense that imagine you actually know what this nature is, what you should be doing is to actually predict the probabilities from which these outcomes are being generated. So that's your truthful forecaster, and that's an option for a forecaster. But the second algorithm, which is what Foster-Bora and everybody else thinks about when they think about sort of calibrating asymptotically, is more about covering up past mistakes. And in particular there, you don't only think about what you know about the world, you also look at the realized outcomes, as you should. And what happens is that maybe you start predicting 0.5, and then some outcome is generated and happens to be rainy that day. What you might do next time is purposefully make a mistake. Predict 0.5 again, because you know that you're going to correct the bias that was incurred to you on time step 1. And then time step 3, you just go truthfully again. The same thing can happen on this side. Let's say that you again predict 0.5, and it so happened that it wasn't raining that day. So again, you incurred a bias because you're predicting something that's a real value and there is some bias coming up. And then you try to correct it again later on when you're sure that you can correct it using this deterministic outcome. So what this means is that if I now try to evaluate these two, the evaluator doesn't know the nature. So it can only evaluate based on the actual realizations. The ECE is going to get the ECE of truthful calibration is going to incur, truthful calibration is going to incur the actual variance because the outcomes are not deterministic. So you're going to pay the variance of the sequence. So you're going to have root T variance. But the ECE of the second algorithm, which is covering up the past mistake, is 0 because you covered every bias that you created.
Is there a reason why you use the word truthfulness instead of accuracy?
I think accuracy can be described by the, still something that looks more like bias. So when I talk about truthfulness, it comes from the economic language where the minimizer of your CM has to be the underlying generator. So truthfulness in general, that's what it means rather than capturing lack of truthfulness. It's like are you truthful or not? I mean, accuracy, I think people might disagree. Like calibration, people sometimes think about it as a notion of accuracy as well. Okay, so the issue here is that ECE is essentially gameable. And the reason we really don't like gameable things is that, once a measure becomes what you're actually using as a target, it ceases to be a good measure. This is famously known as Goodhart's law. So what we are hoping to do is to essentially design calibration measures that do have the soundness completeness. They are reasonable calibration metrics, but they're also truthful. Okay, so what does truthfulness mean? To study that, we study this hypothetical scenario where the forecaster knows the nature, and this nature is some joint distribution over T time steps. Then the truthful algorithm is the algorithm whose predictions are exactly the conditional distribution of the next outcome. So you're predicting truly that P star of T. The optimal calibration or optimal predictor is the mapping from what you have observed and predicted in the past, so your history, to your next predictor, such that it minimizes the calibration measure that you chose in expectation. We say that something is truthful if the minimizer, like the best, the optimal, is indeed truthful. It's hard to capture that exactly, so I'm going to capture it with some kind of a multiplicative approximation. We say that a measure is alpha beta truthful if the loss of the truthful forecast as measured by that calibration metric is no more than some alpha multiplicative plus beta additive term on top of the optimal. Yes?
I'd be curious, could you comment on the relationship between this definition and proper scoring rules?
Perfect. Just hold on for 2 slides.
Actually, sorry, I'm confused about something. So for this optimal prediction, why wouldn't you use look ahead? I mean, somehow here, the definition of what the person's doing is greedily choosing the PT that minimizes CM. Mm-hmm. In principle, depending on the CM, shouldn't I use more foresight to?
Because the way that I like to at least think about optimal prediction is what the evaluator is doing as well. So for optimal prediction, I want the evaluator to be able to say that this was a good choice. It was optimal in that sense. So when we think about optimal forecast, we're really thinking about it in terms of what the evaluator would be rewarding you. That's why we are not doing look ahead. So we are not making a hypothetical situation that you actually know the underlying generator process.
Okay.
Make sense? In some sense, while the truthful is for a scenario where the forecaster is Bayesian and everything, the optimal is what you can actually evaluate someone based on. Okay. And that's why we want it to be something that the evaluator can measure without knowing the underlying distribution. Okay, so the first thing we do is we take all the calibration measures essentially that people have been talking about and try to put them on this axis of completeness, soundness, and truthfulness. So this is what we see. The ACE one, in fact, what I showed you was indeed something similar to saying that there is a additive gap of omega t. You can make it a little bit worse what I did. Can I just 1 second? But ECE, while it's probably the most popular one, there are many other calibration measures. So smooth CE, we'll talk about it briefly, is when you try to make the boundaries of the bins a little bit more smooth. There is a this is thought about as actually distance to calibration. U-calibration is a different type of calibration. It's usually for downstream decision-making and swapper grid. Then all of these are essentially complete and sound. And what their problem is more in the gap for truthfulness. And if you look at it, the truthfulness gap is always either some linear term as additive, or you're paying some constant terms in terms of the gap. With one exception, proper scoring rules. Somebody was asking about proper scoring rules. So proper scoring rules, their problem is that they're actually truthful by definition, but they're not sound and complete in the sense that they don't reward almost correct, or penalize incorrect things well enough. So they don't meet this little OT, omega of t kind of separation. And then what we give, our contribution here is that we give something that is both sound and complete, and its truthfulness is just multiplicative. So like for some constant, universal constant C, you have a multiplicative truthfulness. So the next thing I want to do is to really talk about how would you go about actually designing this thing. How much time do I have?
You have like at least 12 minutes.
Perfect. Okay. So I want to talk about design principles for how to actually design these calibration measures that are sound and complete to start with, of course, but they're truthful, with the truthfulness being our focus. So just a reminder, this was ECE. So let's look at what went wrong with ECE one more time. What went wrong with ECE, and you could actually make this even worse, is that imagine the scenario that you have, the nature, flipping coins with P star I, and these P star I's are all very, very close to 0.5, but they're not exactly 0.5. So now let's see what ECE would have done. ECE of the truthful is going to actually be really large. The reason is that the truthful predictor never makes the same prediction twice. So essentially every prediction is in its own bin, which means that it's paying the maximum variance for that one-time step. So all of its errors, they never cancel each other. But of course, the optimal thing would have been, which is like non-truthful, would have been to say that, oh, I'll just go with their average. And if the average was close enough to 0.5, all of those mistakes you made would eventually cancel each other, and the variance would have been root T. So what really was the problem here was the discontinuity at the level of a bin. The fact that if you change your prediction a tiny bit, the bin that they were assigned to or what biases they were canceling completely changes. So this is the issue, the sensitivity to the exact value of the prediction. And we are not the first to notice this. In fact, this is a problem with a lot of calibration measures. And it was the reason this smooth CE, a smooth calibration error, was introduced by Kakada and Foster many years ago. And the idea is that you take this, and instead of looking at the absolute value, which is doing the biases, you look at sort of more Lipschitz way of actually deciding where the bins start and finish. So you take these functions, F to B, Lipschitz functions from 0, 1 to the range of -1 + 1. And there are many nice things about this smooth C. I'm not going to go into it, but the primary thing is that it sort of make sure that it's not too gameable by just deciding exactly to move your prediction by a tiny, tiny bit. Okay, so that's one problem. And the solution to it is the smoothness. The second problem is, let's look at sort of what went wrong in the example I gave you, again, about ECE. And the problem here was that you could really decide exactly how to correlate with the decision you're making right now with the past, in order to cancel the bias. In some sense, you knew exactly which bias in the past can be corrected with actions you're taking in the future. And the issue here is that the forecaster knows exactly how their errors are being evaluated across time. How would you face this? The way we think about this is that, well, what if I evaluated this forecaster on a randomly selected subset of time? Now, he doesn't exactly know if the actions he's going to take today are going to cancel a bias that I counted or not. So there is like a little bit of a trade-off between lying and actually sort of being truthful in terms of canceling past bias. So this algorithmic principle is what we refer to by subsampling. And subsampling essentially says that you pick a random subset, uniformly random, subset of time steps, and you look at the expected value of whatever calibration measure you were looking at as expectation taken over which time steps is being evaluated on. And in particular, we are combining algorithmic principle 1 and 2, which leads to subsampled smooth calibration error, which is essentially smooth calibration error as defined in the previous slide as measured on a random subset of times. Okay, any questions about these two algorithmic principles? Okay. So the theorem that we have is that if you take this subsampled smooth calibration error, and mathematically, the way I like to think about this is that you had the smoothness is this function f of pt, and yt is just a 0, 1 indicator of whether you're counting it in your counting that time step or not, and you're sampling it from Bernoulli half. And if that's the measure you're going for, the subsampled smooth calibration error, the value of the truthfulness is no more than some constant, think like 5. It's a larger constant, but you can think of 5 for universal constant with no additive factors. So how might you go about proving, oh yes.
Just a quick question. I wanted to see if you can comment on how this relates to multi-calibration. It's the idea of you're going to calibrate on, various ways of grouping your inputs and measure calibration on multiple overlapping groups. Right. So it seems like here, if you're doing randomly selected time steps and maybe do several random selections.
Yeah. So it's related. Here's the differences I see. It's quite important that we are taking expectation over y. If you were gonna do worst case over y, for example, you cannot, so you still get a measure that has some properties, but that's not a measure that you can actually get no regret with respect to. Like you cannot have little O of t. So I would say the significant and important difference here is that you're not looking at the worst case choice of something, but which is the more common way of thinking about multi-calibration, and some other related work also by, I think, Haghtalab and Foster that looked at sort of other measurable sets. And you're looking at expectation of these things. So that would be the relationship perhaps between them. Yeah, and I was going to say that there is one of the things I had on the slide is called U-calibration. U-calibration to me is also more closely related to multi-calibration because you're sort of trying to be calibrated as measured by the worst case of many functions, but it's less so about measurability with respect to past and more so about some penalty functions. But yeah, so it's definitely some relationship, but not directly.
Here's the average case over lots of randomly sampled subsets, or how are you?
Right. So in mathematical definition is actually the expectation. If you want to do this, like you want to actually create error bars, you can just truly subsample like some polynomial many and it would be a good estimation. Is there another question? I feel like I saw another hand, but okay. Okay, so what I'm going to tell you is, I don't want to go into the proof details of this, but I think it's a good exercise to even think about how you would prove this thing because it's quite involved. And part of the challenge is that really the idea here is that you have to identify some sort of a complexity of your data generating process and make sure that the optimal and the truthful calibration error can be quantified with respect to that complexity measure. The natural complexity measure we think about is this kind of like an empirical variant. It's like a variance notion where we really think about this as sort of the conditional variance when you keep conditioning on the past. And the square root of that is sigma is what we are really thinking about. And what we really show is two facts or two lemmas. The first is that the optimal value, of the SSC is lower bounded by omega of this complexity measure. This is actually kind of intuitive, maybe not exactly as a multiplicative, but you should feel like something like this enters the picture. And the reason is that the performance of any forecaster, including the optimal forecaster, is going to be limited by the inherent randomness and noise in this YT. So because YT is independent, it makes sure that some of the variance that's in the actual underlying sequence translates to the variance in the measure that you're working with. So this is kind of the underlying idea for why optimal, or actually the error of any predictor, would be lower bounded by this complexity measure. On the other hand, the truthful one is also measured by this. It's not much larger than this. This is a little bit more sort of intuitively harder to see, perhaps. But in fact, this is true not just in expectation over the time, but it's true for the original smooth CE, the one without randomness of YT. And one way I like to think about this is that if I took this F and I actually made it a constant function, like kind of like ECE, in fact, then this is bounded by the variance. Now, what you have to show is that constant function, if I change constant function and take it to all one Lipschitz functions, I didn't make this much worse. And that idea is just kind of saying that the class of one-dimensional Lipschitz functions are not significantly richer than the class of constant functions. And you can sort of think about your learning theoretics toolset. You kind of use a covering idea. You bring like chaining arguments in. And all of those things come together to say that, well, this is bounded by some notion of variance. So this is the two ideas and two technical lemmas, quite involved to actually do them. But the idea of the introduction of this complexity measure is quite simple and seems like the right way to measure how the complexity of your data generation comes to your actual evaluation. Okay, let me wrap up. Essentially, this talks that the calibration measures are supposed to quantify the reliability of predictions. But if you think about reliability as being a notion of truthfulness, that's not the case. And then we said that there are two principles that come together, subsampling and sort of continuity, that make a truthful calibration measure out of one that wasn't truthful. Couple more comments on this is that this is a nice calibration in the sense that it's also a doable thing to do. So even if the sequence was unknown or adversarially generated, you can actually have SSC, like an algorithm that gives a little OFT SSC. And I like to think about this as almost like a best of both worlds type of guarantee that says that if the forecaster knew the underlying data generation process, it will be truthful and will give you the actual prediction probability of the outcomes. But if the forecaster was not aware of the underlying, and in fact, maybe the underlying data generating process was just an adversarial sequence, the forecaster still meets the no regret property. And that's what I like to think about this truthfulness plus soundness, completeness, plus the regret as a notion of best of both worlds. That's all I really wanted to say. If there are questions, I'm happy to answer.
Time for a quick question.
Yes, so I don't know whether it's a very specific question, but is it clear that this smooth CE is easy to compute because it's reading us the maximization of this function space?
Compute in the sense of
the value of this measure.
So it's very, so if I'm given, it's quite easy to compute a good upper bound for it. Can I compute it exact?
At least for regular smooth calibration error, we can do it in nearly linear time now.
There you go. Okay, good answer.
You can show it's equivalent to some min-cost flow problem because it's like Lipschitz constraints. So you can just use min-cost flow solvers.
Okay, so then you can take that, and the subsampling is just an estimation problem with polynomial samples. You're good.
But there's no closed form solution to that.
I guess if they have a good way of doing, yeah.
You can solve it very quickly and exactly.
Yes.
Absolute constancy, is there a hope to reduce it to something close to 1?
Our lower bound is pretty high constant and it's pretty generalized. I'm not super hopeful, but prove me wrong and I will be very excited. Yeah, sorry. Yeah.
So does this extend to the case where the events are not binary? You have maybe multiplets?
Yeah, we didn't do it in the paper, but it feels like all the principles we have very naturally go through when you're doing a high dimensional. Another last one? Yeah.
Is the idea kind of that you want the forecast to be conditionally independent given the outcomes? you're kind of doing a whether this inference is holding or not.
I think it's not just that, because the smoothness is also an important aspect of it. I think that's one part of it, you know, saying that you're not just trying to correct past mistakes, but I think that doesn't really explain the need for smoothness, and smoothness is quite fundamental as well. I think the two have to come together in terms of where you're, like, you don't want to just be correcting past mistakes, but where did the past mistakes happen is also important. Was there one last one?
Thanks again.
Okay, thank you.